All right. Well, I'll do a little intro for Prajkta, and then I'll let her tell you more about herself and her background. But this is Dr. Prajkta Mane. She is what doesn't really matter, but it's what we call a visiting scientist at LPI, Lunar and Planetary Institute here in Houston. Though she sits most of the time over at Johnson Space Center when we're allowed in buildings, anyway. So anyway, she's gonna tell us about the big questions surrounding asteroid/meteorite. Meteorites. They're driving that kind of science and exploration.
All right. Hi, everyone. I am a postdoc visiting scientist at FBI, and I also am a geologist by training. I have a PhD in geological sciences, but I technically studied space rocks. So that's kind of a geology, but most of my research is lab-based, where we already have the samples. We study their compositions, isotopes, structures, mineralogy, etc. So today I'm actually going to give a brief intro about what cosmochemistry is and amazing discoveries that have led to our understanding of early solar system, or how planets, etc., formed from these samples, and how we can study them, etc. And then I have some questions that, like, overarching, outstanding questions that is something for the students to think about, so that they can come up with their own project. All right, I'm going to share my screen.
And real quickly, while she's bringing that up, just want to make that point again. What she just said is that, again, the whole idea with this presentation and the one on Tuesday about the moon is to help you all, possibly help you all come up with a research topic to pursue after you finish all your 101 stuff. These presentations, along with other resources, the 101 things themselves, all of these things together, I hope will help you. And plus then discussions with your advisor, of course, once you really get to that point, to really help you narrow down that topic, what it is you're going to specifically look at. Okay.
I do have a request. As I'm going through this presentation, if you have any questions, please stop me and ask them. Unfortunately, as I'm sharing my screen, I can't see the chat. So just unmute yourself and ask. This is all super friendly. I don't mind if you interrupt me, so please do.
Or conversely, if you want to put something in the chat, do so, and then I'll ask it for you. Or again, also just speak up. I'll leave it up to you all.
Yes. All right. Perfect. So can you see my screen?
Mm-hmm.
All right. Perfect. So I'm going to talk about meteorites and the early solar system. All right. So the evidence of meteoritic delivery is very common on most terrestrial and planets, including Earth. There is a very famous example of a impact crater where a meteorite crashed around 50 to 60,000 years. This is right in Arizona, actually, in the United States, close to a city called Flagstaff, where you have this giant hole in the ground, approximately 2 kilometers in its diameter. And this impact happened around 50 to 60,000 years. It's a very famous example about how meteoritic impact is common on Earth and many other terrestrial planets. And the second image that I have here is the comet Shoemaker-Levy, which impacted Jupiter in 90s, I think 1994 or 96, something like that,
Yep.
and had this spectacular phenomena where, as it entered into onto Jupiter, it burned and created these amazing images. So meteoritic impacts are very violent, very exciting if you're studying them from far. Probably not very good if you're actually experiencing them from very close, like the dinosaurs. But I am really interested in meteorites, or the materials that these impacts bring in, because they tell you really exciting stories about how our solar system formed, when did it form, and how we got where we are right now. So here
Prajkta,
is
I'm sorry. I'm sorry.
Yes.
We just had to wonder if you could talk a little louder, or maybe just get a little closer to your mic.
Okay. Is this better?
Is that better? No. Oh, okay. Okay, great.
No?
Thanks.
Okay. I'm actually going to check the settings because sometimes Zoom does something weird. Okay, let me see. I'm going to stop sharing for a second.
Sure, no problem.
I haven't used Zoom in a long time. So sometimes it does something with the microphone settings.
Yeah, go there's a little arrow next to the start video button. Click that little arrow and go to your video settings, and you should also be able to access your audio settings from there too.
Yes, can you hear me okay now?
You sound good?
Okay. Yeah, the volume actually goes back to normal or some default setting and things go crazy here. All right. So where were we? All right. So most of the meteorites and the astromaterials, materials that did not form on Earth, we call them astromaterials, they formed really very early in the solar system history, like 4.5 billion years ago. And majority of them formed kind of close to the sun. So here is a like it's a cartoon of what the early solar system probably looked like. So you have the proto sun in the center here, the baby sun, and it is surrounded by a disk of gas and dust. This gas and dust then slowly comes together to form dust bunnies that come together to form larger and larger planets. But this is the time period in our solar system history that these meteorites record. So meteorites can be classified based on like their composition in three categories. You have stony meteorites, you have iron meteorites, which are mostly made of iron and nickel, and then you have stony iron meteorites. The stony meteorites can be classified in two different groups by themselves based on how they form. So you have the chondritic stony meteorites and achondritic stony meteorites. So this is based on how they form. So like I explained earlier that when the solar system was basically a giant disk of gas and dust that was basically revolving around the sun or orbiting around the sun, many of these and the temperatures were the temperatures were really hot. As the temperature started cooling down, the material condensed into solid dust bunnies. They came together, underwent some processing, but mostly remained pretty pristine and did not undergo any large scale melting. So these rocks are basically compared to similar to sedimentary rocks that we find on Earth, that are aggregates of different materials that formed at different times. But they're primitive. After their formation, not many processes have affected them so far. So those are the chondritic meteorites that you see over here. Iron meteorites, so now when meteoritic bodies, as they accumulate more and more material, they get really large. And as they get larger, the accretionary heat and also the radioactive heat starts melting them. And when this melting process happens, as the meteoritic parent body has completely melted, all the heavy material like iron and nickel goes to the core, and the lighter material, which is silicate, that remains on its mantle or its crust. So when such parent body or asteroid is broken apart, the central material, which is mostly purely iron and nickel, is that's where these iron meteorites come from. Whereas the achondritic stony meteorites that are shown right here are basically part of the mantle, which is made of silicate material. And there's somewhere between the core and the mantle boundary, you would find a region where you have silicates as well as the iron, which is mixed up, and they form these beautiful meteorites. That region forms these beautiful meteorites that are called pallasites. So this is a general overall classification of meteorites. Most of the meteorites, so where do these meteorites come from? We have so many of meteorites in our collection. A large majority of these meteorites, they come from the asteroidal belt, which is between the Mars and Jupiter. And here are examples of a bunch of different meteorites that have been imaged that we can see through telescopes and different space missions that are shown right here. There are around 150 meteorites that come from the moon, and we have the evidence for that, and about the same number of meteorites that also come from Mars. Other than meteorites, we have some other astromaterials in our possession that can be used to understand different histories on some planets or planetary bodies or how they formed. So the first one is a sample, which is samples that are returned from the moon by Apollo and the lunar missions. So here is an example of an Apollo rock or the moon rock that we have in our collection. There is another sample return mission, which was called Stardust mission, that actually went to a comet and collected material that was ejected from the coma of the comet and captured it in this aerogel material. So these are tiny little dust particles that have been captured and they were brought back to Earth. So we also have some samples of cometary materials in our possession. The third mission that also brought samples back to Earth is the Genesis mission. So this mission actually went to the Lagrange point of Earth and sat there and collected solar wind samples to study the chemical and isotopic composition of the sun. So these are first three sample return missions and their examples. We also have interplanetary dust particles. These are few micrometer aggregates of materials that you can see here as an example. So there is constant dust that has been formed in our solar system by breaking up and impacting asteroids or even comets that bring in material. So all these materials are captured in Earth's atmosphere, and these materials are preserved and are available for us to study. And the fifth type of example that I want to discuss here is the micrometeorites. These are tiny particles that are basically survive entry into the Earth's atmosphere. They're a few microns in size, and they can be collected and studied and analyzed to understand how different parts, different planets and materials in our solar system formed. So I am a cosmochemist. I study isotopic composition and chemical composition of these different materials. These materials can be analyzed for their chemical composition, so different elemental abundances, different isotopic composition, sometimes to date them or to understand where they come from, where they formed, etc. Also for their mineralogy and their structure and texture. So some of them are porous, some of them are very compact and stuff like that. So these are the two primary instruments that I use at NASA JSC. These are called mass spectrometers. So both these instruments have a giant magnet that basically separates out different isotopes of the same element into they separate out based on the magnetic field, and then you can analyze the isotopic composition of these materials. But they are slightly different. The first instrument, you take a bunch of rock, and you dissolve it completely in harsh acids. And as you have these, and then separate out different elements and then introduce them in the form of solution. So this is a solution mode example of the instrument, which gives you really high precision isotopic data, where you can see tiny little differences in the isotopic composition. The second instrument I have here is called Nanosims. This is not as precise as the first one, but what this does is it allows you to do in situ analysis. So you just take a slab of rock and then go really like high spatial resolution of few hundred nanometers to maybe a couple microns. So when you have really tiny particles and not much material, you can actually point and shoot the ion beam where you want to analyze and still analyze the isotopic and elemental composition of these different materials. So these are just two examples. There are multiple examples and analytical techniques by which you can analyze these rocks. So I've decided for this talk to discuss some of the major discoveries that actually changed our understanding of how Earth formed, how solar system formed. And I'm just going to give some examples of those discoveries. So one of my first and favorite example is how old is the Earth. Now, as you can think about Earth, it's a very active, very violent planet. You have a lot of activity. You have volcanism on Earth. You have plate tectonics on Earth. You have lots of weathering happening, soils and trees growing and human civilization and a bunch of things. Therefore, it's very difficult to find a rock which is very pristine, the oldest rock on Earth that can tell you how old the Earth is. However, we can actually determine that based on meteorites. So if you remember the first image that I showed where there was a proto-sun at the center and the disk of gas and dust, that was the common planetary disk that probably formed all the planets. And the materials that survived from that era in planet formation are some of these meteorites, specifically the iron meteorites. So remember the meteor crater that I showed you earlier? That was actually the culprit to form that crater is this Canyon Diablo meteorite. It's an iron meteorite, and iron meteorites are actually special because they don't contain much lead. So we can date these meteorites using the uranium-lead radioactive system. As you know, uranium is, you probably know this, but uranium is a radioactive element. Two isotopes of uranium are radioactive that both decay to lead. So the lead 207 and 206 are the radioactive decay products of the uranium 235 and 237. And as you form these, as the uranium decays, the amount of both these isotopes is going to increase in this direction. So any meteorite that has a lot of uranium and not much lead is going to fall somewhere here, whereas any meteorite or any sample actually that formed at the same time but has less amount of uranium, but actually a lot of lead is going to fall somewhere here. So when you analyze a bunch of iron meteorites that contain a lot of uranium, they're going to give you a line or a correlation, which is called an isochron. So based on these analysis of these iron meteorites and using the uranium lead or lead system, as we call it, Claire Patterson in 1956 actually determined how old the Earth is. And the age of the Earth, according to his analysis, was 4.55 plus or minus 0.07 billion years. So after so many years, like 70 something years, this age has not changed much. We have put more decimal points after that, maybe to be a little bit more precise, but the age of the Earth that was determined so many years ago based on meteoritic analysis is actually very accurate. I hear someone's mic coming off. Does anyone have a question?
Well, actually, I had just a comment and then a question. The comment is just that, so referring to your Canon Diablo image there. So the actual, that's a piece of it. The entire meteorite was what, 25 meters in diameter, 50 meters in diameter?
Yeah, like imagine the size of a school bus, maybe.
Yeah. Okay. So that was the size of the original entire thing. But they do find fragments here and there of the original. If you ever have a chance and you're in northern Arizona, you should go to Meteor Crater. It's a place. It's actually run by the family of Daniel Beringer, who did the first serious studies on the crater. So there is an admission to get in, but a charge. But it's pretty cool if you have a chance to go check that out. My question is, why uranium? Why do we look at uranium in meteorites?
Right, that's a very good question. So how cosmochemists determine age is we use radioactive elements. Uranium has two, and I'm completely blanking on the half-life of that element, but it's a long-lived radionuclide, meaning you still have a bunch of uranium left that even if some of it decays to lead isotopes, you can actually directly measure the isotopic composition of uranium as well as lead. So uranium decays to lead, and it has two different isotopic systems because there are two different decay schemes. So that can give you a very accurate, more powerful isotopic composition and therefore ages. So other than uranium, you have some other isotopic systems too, like you have samarium, neodymium. I'm going to talk about 26 aluminum, which is a short-lived radionuclide. So there are a bunch of options, but uranium is the most robust and powerful system because you have two different uranium isotopes that decay to two different lead systems. So when you're analyzing them, you don't actually have to measure the uranium isotopic composition. And it gives you a much more precise analysis and much more, like, the error bar that you see here of 0.07 billion years, it can, with analytical techniques now, it can even be shortened and give you much precise answer for your age. All right.
Hey, thank you. Yeah, and actually, Gene just put a comment here. Uranium-238 decays to thorium-234. Is that what you were trying to think of?
So there is a decay scheme. There are multiple isotopes that decay to different things, but there are two. I think it is 237 and 235, but I'll have to double check. I'll get back to you on that after the talk. Is that okay?
Oh, yes, yes. Please continue.
Cool. So now you know how old is the Earth. How old is our solar system? What are the first formed things that formed in the early solar system that that we can analyze? So remember, I talked about these chondritic meteorites, the stony chondritic meteorites. They're basically the earliest materials that never underwent any differentiation. So they are like sedimentary rocks that were preserved in the early solar system and in the form of these meteorites. So specifically, you have these things that are, so the term chondrite comes from these chondrules, which are these round objects that you see. They are around centimeter to millimeter sized droplets of like molten rock that were floating around in the early solar system. But the other objects that you see here is something called as a CAI, or a calcium aluminum rich inclusion. And here is an example of a relatively larger CAI, which is kind of irregular in shape. Since it is rich in calcium and aluminum, which are very refractory elements, if you like imagine a gas of solar composition, which is so hot that everything has evaporated and things are slowly cooling down and condensing, the first things that condense out, or the predicted to have condensed out of this solar composition gas, is very similar to the mineralogy of materials that we find in these CAIs. So they have been thought to be the first form solids in our solar system, and they can be dated using different isotopic systems in our solar system. So these are the materials, like meteorites are called poor people's space probe, because it's really expensive to go get these materials from the asteroidal belt or from the moon or Mars, but we already have this sample in our possession. And they tell you a lot of interesting mysteries of how things formed and when things formed. So here is an example of one such CAI that was formed 4,567.30 million years ago with an error bar of 0.16 million years. So this is basically 4.5 billion, but since we are talking about million, the decimal point has moved a little bit. And this is not just one CAI, but there are multiple CAIs that have been analyzed. So now Andy asked about uranium lead or lead-lead system. That's right here. That gives you the age of the CAI that has been defined here. But then there are different other isotopic systems too, like 26 aluminum, 26 magnesium, or 53 manganese, 53 chromium, and hafnium tungsten. So different isotopic systems, radioactive systems that decay, and you can measure the isotopic composition of materials based on those systems. And they all kind of give you the same answer. So the oldest dated solid in our solar system shows this age. Sometimes it is a little bit difficult to understand or like imagine ages that are beyond our 10 years or something, because human lifespan is not really that big or that long. So here is an example of this comparison. Like if you have a person who's say 60 years old, for some reason they have lost their memory and birth certificate. It's like determining the time of birth for this person with an error bar of 8.4 hours. So we know the age of our solar system very precisely with like that precision for a human being. By the way, biology cannot do that. Based on your like the enamel coating on your teeth, you can, I think, approximately do that for 2 to 3 years to determine someone's age. So we know the age of our solar system much more precisely than what we can say about a living human being. And that is all thanks to these meteorites and the CAIs that are found in these meteorites. All right, so the next big discovery is existence or discovery of pre-solar material in these meteorites. So most of the meteorites that we talked about earlier, like the iron meteorites or the achondritic stony meteorites, they have undergone differentiation and kind of a homogenization. But when you look at these chondritic meteorites, they're basically like, aggregates or sedimentary rocks of material that existed in the early solar system. However, many of these meteorites that have not been processed later contain like micrometer to nanometers, few hundred nanometer size materials that we think come from different stars, like stellar systems other than our sun. And therefore we call them the pre-solar materials. So here is the first discovery, or actually hint of what a pre-solar material, like some meteorites included pre-solar material that came from out of our solar system. So here you have a noble gas isotopic signature, which is the neon 20 to 22 isotopic ratio. Most of the solar system material falls between this gray bar, but some of the meteorites, when you take them and heat them, they release the noble gases or different gases that are inside them. And some of these gases at certain temperatures, like 1000 degrees, actually show a very significant deviation than what Earth composition or the terrestrial or solar system composition is supposed to be. So this was the hint that some of these meteorites contain maybe tiny phases or tiny minerals that did not form in our solar system and they came from outside. And then this was like 1969. But then with the advent of instruments like nanosims that I showed you earlier, and different analytical techniques, you can actually see a bunch of isotopic materials. So now I'm going to first talk about this plot that analyzes oxygen isotopic composition. Oxygen has 3 isotopes, 16, 17, and 18. And you see these dotted lines, they intersect over here. That is the composition of Earth, all the bulk meteorites and all the materials that formed in our solar system. But these tiny little pre-solar grains, like this is a silicon carbide with like approximately a couple microns in size, or graphite grain, bunch of other silicates and oxide pre-solar grains, they form, or they show an isotopic composition that actually deviates significantly by orders of magnitude. This is a log-log scale, so orders of magnitude from Earth's composition. So no physical or chemical process within our solar system can actually form these huge isotopic variations in the materials. However, there are models of different like nucleosynthetic sites, that is where these elements form in different stars like AGB star or supernovae, etc., that can actually reproduce these isotopic compositions. And that's why we think, based on isotopes, that these materials come from outside of our solar system, forming in different stellar environment, different stars, and then being deposited back onto the Earth somehow. So these meteorites formed 4.5 billion years ago, but this is not like just a phenomena that happened 4.5 billion years ago, but stop. Here is another very exciting discovery of actually astronomical observations or astrophysical observations, where they found one supernova that exploded 3 times and had these concentric rings, and the evidence of similar things and the material that was ejected from that supernova. But there are these really interesting rock formations on the ocean beds that we find that are called ferro-magnesium nodules. So here is an example of such nodules. So this is basically materials that are deposited in the form of concentric rings. Like, you have tree rings. So you can see the concentric circles that are deposited, and a nodule like that will take like a couple million years, or maybe like more than like few million years to form, as far as the conditions are not disturbed. So these are sedimentary nodules that form on the ocean beds. And when you analyze isotopic composition of these nodules, you do have evidence of materials like that are formed in a supernova. So IN60 is a short-lived radionuclide. It is not synthesized anymore, at least in our solar system. The only place where it can form is a supernova event. So here is an example of like one such spike of IN60 that happened around 2.5 million years, and then another one around 7.5 million years, based on these the analysis of these nodules. So we know that the stellar material or the stardust is constantly brought onto the Earth, even through recent times. All right, I'm going to move on to the next topic or next exciting discovery, which is how do planets melt, or why do we think they melt? So there was one example of a radioactive element, uranium, that decays to lead and forms different isotope and forms lead isotopic deviations. However, because of its long life, it actually the decay of uranium is too slow to actually melt a planet. So uranium is not a main source of heat that can melt a planet. But there are many other radionuclides, short-lived radionuclide systems that can actually decay and produce heat. One of them is 26 aluminum. And here is the first discovery of existence of this. So they have been hypothesized to be existed in the early solar system. But here is the first analysis that actually showed that, oh, it actually did exist. And we can see the evidence of them in these chondritic meteorites. So what you see here is 27 aluminum, which is a stable isotope of aluminum, and 26 aluminum is completely decayed now, which is a short-lived radionuclide. And it decays to 26 magnesium. So therefore, every time you will have 26 aluminum decayed, it's going to increase the isotopic signature of magnesium in this axis. And as you can see, it forms different isochrons, or the correlations where it shows evidence of decay of these short-lived radionuclei. So this provided an evidence that there was 26 aluminum that existed in the early solar system, and it probably this was brought onto the Earth or to our solar system by some stellar sources, and it also probably occurred as a principal source of heat that caused melting of different rocky planets. This can also be used as a potential chronometer. So this was one example of how Earth formed and how other solar system formed. But since we have all these materials, like we have CAIs, we have contours that millimeter to centimeter size, round objects that we saw, then we have meteorites from Mars. We also have materials that are differentiated, like the iron meteorites or the stony meteorites. So we can date all of these, and they can actually tell us very precisely, and they can tell us when these different objects on the materials formed. So here is time zero, which is 4,557 million years, which is the time zero defined by the CI formation. And with respect to that, you can see that there is differentiation happening. There are chondrules that are melting. So all these processes that are recorded in the early solar system approximately simultaneously as in different parts of our solar system. So analysis of these meteoritical materials and isotopic analysis specifically can date these materials and tell you these when different parts of our solar system formed. So now you know when some of these materials formed. Do we know how they formed? So there comes the stable isotopic analysis of different meteoritic materials. One of the very famous examples is oxygen. I hope you remember the earlier plot that I showed you about pre-solar grains. So now what we have here is the isotopic variations that you find on Earth, on terrestrial samples, or even meteorites. They are really tiny. They're like, up to 4th decimal point. So what we do in order to understand them well is we actually normalize them with the Earth's terrestrial composition, and then we multiply them by 1,000 so that every variation that you see is kind of exaggerated. So these are really tiny variations in isotopic composition. It looks like I lost my cursor here. But even with these tiny variations, we do have analytical technique size enough to see these variations. And as you can see, different meteoritical materials form on in different regions, and they tell you that they did not form from the same starting materials based on the oxygen isotopic composition. But oxygen is not the only material, but there are other isotopic systems that can be analyzed. Like, for example, we have chromium isotopes. So now you have chromium and oxygen both plotted that show that most of the materials that formed in our solar system and that are sampled by the meteoritic collection actually form into different distinct groups. So one of this group is called carbonaceous, and the other one is called non-carbonaceous. So most of the materials form these two different groups. So how can you explain something like that? So here is one hypothesis. There are multiple ways people have try to explain this isotopic dichotomy that you find in the early solar system. So one of them is early formation of Jupiter. So if you start making these smaller meteoritic parent bodies, and then you form a giant planet like Jupiter, it's actually going to clear out a gap in the early solar system and separate out the materials that won't mix with each other and create this isotopic dichotomy. And the example of such giant planets, gas planets creating gaps, are actually being observed in other protoplanetary disks. So here is an example of protoplanetary disks. So this is the stage our Earth was like 4.5 billion years ago. But these are other systems that can be imaged now using really high resolution telescopic arrays on Earth. So this example is ALMA, which is based in Chile. And they have been really successful with high resolution imaging of these different disks. And as you can see, these disks have different sort of structures in them. Some of the round gaps that you see, they probably formed because of formation of some sort of a giant planet in them. So now we can compare what we see in the meteoritical record with what we can see in the other planetary system and get a better understanding about how planet formation process takes place. So I'm going to move on I'm going to actually take a pause here if you have any questions about things that I have discussed so far. before I move on to a slightly different topic, which is the Martian meteorites.
One thing I'll just say is, number one, that's a really cool graphic on the right, by the way, especially given the explanation of how it fits in with the models on the left. You know, so when I was in grad school, I was an education major, but I did a minor in planetary science. So I got a really good education in kind of qualitative solar system stuff. So, you know, I know things about, I learned a lot about individual places in the solar system. It wasn't really until I got to LPI that I really started to appreciate being able to see the solar system as a system, and not just this thing that has these different bodies. And I've really come to appreciate a lot more meteorites. Meteorites used to scare me because the language is so different from just, you know, talking about you know, geologic features on the Mars and the moon. I mean, they're similar, so it's easy. But meteorites would scare me. But I also understand now how important they are. You know, like Prajkta said, meteorites are the poor person's space, you know, space flight mission. It's just I mean, it's almost difficult to have talk about the rest of the solar system if you can't understand meteorites and can't talk about meteorites. So I just wanted to say that I just have a much more deep appreciation for meteorites than I used to, and I still know very little.
I think that's the case for most of us too. We still don't know enough to answer all the questions, and every research problem that you try and understand and like get more data, I think sometimes rather than answering questions, it like giving you answers, it opens up more questions and confuses you altogether. So it's really cool that we have all these astronomical observations or remote observations of different planets, but then we also have these actual samples that we can put into our mass spectrometers or different other instruments like, you know, microprobes, electron microprobes, etc., and actually see on a very small scale, micrometer I'm sorry about that, to say like millimeter scale, and then compare with these giant astronomical scale objects that you can see. So it's actually really cool that not only we can observe them based on the telescopic data, but also actually analyze them in the lab at a very different scale. All right, so we have had many missions going to Mars until now. However, we have not had a sample return mission. There is one which is right now collecting materials on Mars. Right now the Perseverance rover. However, we have not returned samples from Mars yet. But we already, I'm sorry about that. I'm already, okay. Sorry, I have lost control of my computer and my mouse.
Oh, geez.
I can't see my cursor for some reason, and Zoom does this to me all the time. Anyways, so we already have some samples from Mars, but how do we know that these meteorites that came here on Earth are from Mars? So,
Prajkta, I'm sorry, would you like me to, I have your slide. Do you want me to share them on my side and I can advance for you?
That's okay. I may have made a couple changes in the next couple slides. So, but is this bothering or is this okay right now?
Well, we see the meteorites from Mars ? Slide.
Yeah. Good, that's where I am.
Okay.
So I don't know if you saw the text message notification that popped up on my screen. I hope you did. Okay, anyways, so we do have some meteorites from Mars. And how do we know that these meteorites come from Mars? So these are relatively weird meteorites compared to most of the other meteorites. And so far there are maybe 150 or something. But like I said, most of these meteorites formed 4,500 million years ago, maybe plus or minus, not minus, but plus like up to as young as like 4,550 million years or 45 million years, but not significantly younger than that. However, some of these meteorites that we have in our collection, most of them are like basaltic meteorites, and they're as young as like 200 million years. So from time zero, like today, they formed 200 million years ago. So that is actually very surprising because most of the meteorites come from planetary bodies that are small enough that they underwent differentiation in a very early solar system history. For a meteorite to form this late, you would need a planet which is large enough that it is still undergoing all the differentiation and the processing and remain hot enough to actually produce magmas this late in the solar system history. So that was one clue. What is that planet in our solar system that still exists that is large enough for that? That's not Earth, probably Mars. The second clue actually came from the Viking missions, and this was like nail in the coffin. So the Viking mission went to Mars and did bunch of in situ analysis. It analyzed the composition of the Martian atmosphere and the gases that are and the atmospheric composition, the elemental composition of different noble gases, nitrogen, etc., actually match with the gases that are trapped into these meteorites that we think that come from Mars. So this is like a very obvious example that, or the final nail in the coffin, that we know that these meteorites come from Mars. There are around 150, maybe 160 meteorites that have been identified so far that come from Mars. And we, even before visiting the planet, we already have samples. However, we do not have the geological context of where these samples come from. So that is the major driving force. And of course, we don't sample the entire planet. So these are just igneous, rocks. The Perseverance rover is exploring all the sedimentary formations at the planet, at Mars. So, there are different kinds of materials that form and the different kinds of rocks that form. But we have already sampled some of the Mars and we can analyze the isotopic composition or date these meteorites and chemical composition, etc., from these meteorites. So that was one of the cool discoveries in 1980s. Aha, okay, this is another of my favorites. So I've already talked about CAIs, and my research is actually primarily on CAIs. That's why I get very excited about these objects. So these are the calcium aluminum rich inclusions, which are refractory inclusions that formed in our solar system in the form of like dust bunnies, centimeter to millimeter size objects that came together. The mineralogy of these materials is actually matches. If you like thermodynamically, if you take a gas of solar composition and completely evaporate it and then very slowly start cooling it, the first minerals to condense out of it are something like corundum, which your sapphire is made of, or things like hibonite, spinel, and melilite, not the rocks that we found on Earth, or not the minerals that we find on Earth that are actually very rare. They form like at a very high temperatures, but they exist in these CAIs. And they also know, so based on this, we know that CAIs formed probably very close to the sun in the early solar system history. However, NASA's Stardust mission that collected samples from a comet. So comets are supposed to, or we at least think that they form farther away, like close to Kuiper Belt, and even some of the Oort cloud comets, etc. But many of these comets actually contain these really high temperature materials in them. So this was a very surprising discovery of the Stardust mission, that they contain many CAI-like or Contour-like materials in them. So how is this possible? One of the hypotheses to explain this is that early solar system, as it formed, there was a huge turbulence and mixing of materials for many astronomical units like AUs, where things just got mixed up, and then things that formed really close to the protosun were mixed up in the comet forming zone. So therefore, a really violent start of our solar system is what is predicted by analyzing these cometary samples. Okay, this is probably the last one because I do want to answer all your questions. But many of these meteorites, they they actually have organic materials in them. These are probably the starting materials of life that were brought in onto the terrestrial planet like Earth, and then probably initiated formation of life. So they do bring a lot. So they have a variety of organic materials, and those can also be analyzed and seen where organic synthesis can happen in other parts of our solar system. I'm going to talk a little bit about asteroids because I do have some outstanding questions about asteroids too. So the architecture of asteroidal belt, most of the asteroids that we know, they come from the the region between Mars and Jupiter. So you can see all these white dots. There are some Trojan asteroids. So basically the green line, that the larger circle that you see there is Jupiter. And these Trojan asteroids are the swarms of asteroids that basically follow Jupiter at 60 degrees angle. So this is, and then you have a Kuiper belt. Most of these asteroids, actually, you can study them remotely using their spectral analysis or spectroscopic analysis, and they show different spectra. Some of those spectra match with the meteorites that we have in our collection. So now if you look at this plot here, you have asteroids and meteorites and spectra of different asteroids based on these spectral characteristics. These meteorites have been classified into C-type, M-type, S-type, Vesta type, and E-type. And there are some meteorites that show a closer match to these meteorites, to these asteroids. You can also analyze the population study of these different meteorites. So here you have mass, so basically how big these asteroids are, and the semi-major axis, so basically the heliocentric distribution of these meteorites. And as you can see, there are different, like as you go to smaller sizes, they're all mixed up, but at a larger size, they show distinct zones as you go away from the sun. We have many missions that have been to asteroids or in the process of going to the asteroids. The first three that I mentioned here are actually sample written missions. So basically a planetary mission that went to an asteroid, collected material and brought them back or is in the process of bringing them back. The first one over here I have is OSIRIS-REx, which is going to this asteroid Bennu. It actually collected some material last year in October, and by extending this arm and collecting a bunch of meteoritic dust, and it brings it back to Earth in 2023, I think. The other one is JAXA. So the first OSIRIS-REx is NASA's mission. Lots of collaboration between different space agencies here, by the way. But the second one is Hayabusa, which went to an asteroid called Itokawa and already brought some material back. The second mission is Hayabusa 2, which went to a carbonaceous asteroid, Ryugu, and also brought back material very recently, actually. And the analysis is like very fresh and going on in different labs all over the world. So these are the missions that went to these asteroids and brought back materials. But then there are some other missions that are either that have gone to the asteroids and just did remote observations to understand the chemistry, the composition of the surface, the structure of the surface, etc. So one of them was the Dawn mission that went to two asteroids. One of them was Vesta, and we actually think that the samples called HEDs or eucrites, Howardites, and diagenites, we believe that they come from this asteroid Vesta. So we probably already have samples from this planetary body or this asteroid. And the second one is Ceres, which is much more water-rich asteroid. The second mission, which is in the process of being planned, this has not been launched yet, but it will probably be launched soon, is called Psyche. This mission will go to actually a metallic asteroid, or what we think is probably similar to an iron meteorite. So this is going to be a very cool and unique mission that is going to go and observe this asteroid called Psyche sometime soon. And the third mission that's here is called Lucy. So remember the Trojan asteroids that I talked about, the asteroids that follow Jupiter in its orbit, they're called Trojan asteroids. We don't believe that we really have any samples from Trojan asteroids because they're just so far. So mission Lucy is actually going to analyze or observe multiple such Trojan asteroids. And both these missions have not been launched yet, but they're in the process of being prepared for launch. So outstanding questions. I have a list of like 4 different slides. So I'm just going to try and read them out and maybe explain them a little bit. But these are just some examples. There are so many so many outstanding questions that we have in asteroids as well as meteorites, cosmochemistry, that really need young generations, next generation of scientists to come in and answer all of them. So when you look at asteroids, the NEOs, which is the near-Earth objects, are they dangerous to us? Are they ever going to impact us? So that's one of the major questions. What are the dangers that are posed by these near-Earth asteroids? How has the small body population, or basically asteroidal population, changed and evolved over time? What we see now is what existed 4.5 billion years ago, or was there a difference in their composition or their sizes, etc.? What are the processes that are active on the surfaces of these small bodies? what are the elements that are delivered by to the planets used by these asteroids, like water, organics, other things, because impacts have been so common in the early solar system or even current solar system that we believe that asteroidal impacts or cometary impacts are actually a very powerful mechanism of bringing materials to different planets. So that's one unsolved mysteries as to what materials these asteroids and comets can bring to terrestrial planets. And are they habitable? For meteorites, as you can analyze them in the lab, they also have lots of mysteries that are like contained in them and that need to be resolved. One of them is what are the circumstellar material or the pre-solar grains that contributed to the early solar system. Do all meteorites have pre-solar grains? What are different abundances of pre-solar grains and where do they come from? Um, what are the processes that delivered water to terrestrial planets? Were they in the form of asteroids or comets, or did they already have it as these planets form? What are the sources of organic matters on these different asteroids? Like, did they also bring organic matter? And where does this organic synthesis happen today, apart from Earth, in different parts of the solar system? What are the time scales of planet formation? When did different planetary materials form? How far apart or how close together, or all these questions can be answered by analyzing meteorites as well. And which classes of these meteorites come from which classes of asteroids? So the asteroid meteorite connection is one of the really interesting topic of exploration. And how diverse are these components? Do we actually sample all types of all types of asteroids in our meteorite collection, or are there things that are missing? I didn't really talk much about comets except the Stardust mission a little bit, but comets in themselves are very interesting. They have very different mysteries compared to meteorites and asteroids. So how variable is their composition? How heterogeneous are individual comets? And what are the abundances and distribution of different classes of like asteroids, comets, and Kuiper belt objects in our solar system? So Kuiper belt is beyond planets, but then you have this giant molecular cloud, which is called Oort cloud, which is much farther. And do the comets that come from the Kuiper belt versus Oort cloud, do they differ in composition and structure? Did asteroid differentiation involve all melting and magma oceans, or was it like just little bit of partial melting? Then are there any systematic or chemical isotopic gradients in the solar system as different materials form? And how did this accretion of these different materials occur? Like I discussed a little bit about the isotopic dichotomy in the early solar system material. It's similar on those lines. Do we have meteoritic samples from objects that formed in the dominant feeding zone of innermost planets? So the asteroids, basically this is like the asteroids or the meteorites that we sample today. Are those very similar to what went into the formation of Earth, or were they different? Or this is like, are the asteroids residues of planet formation, or that's something as a starting material, different planet formation? One of the very important question is, how did Earth get its water and other volatiles, and what role the icy objects play in the accretion of these various planets? And then what mechanical processes of accretion up to and through the formation of mid-sized bodies. So one of the barriers of understanding how accretion occurs is it's really easy to form like small little bodies, but then there is something called as a meter size barrier, that once you start getting bigger and bigger bodies, they basically impact on each other and break into smaller pieces. So how do you explain that particular barrier and grow bigger and bigger planets? That's another very important question that has not been solved. So I think this is pretty much it. And if you have any questions or if you want to discuss anything, please go ahead and unmute and let me know.
Okay, thank you, Prajkta.
You're welcome.
So like we learned on Tuesday with the moon, a lot of outstanding questions and things we don't know about the moon. Same for asteroids and meteorites, and really how all of this really tells us, how answers to these questions will tell us so much about the solar system beginnings and its evolution. So anybody, just real quick, does anybody have a question they're ready to ask, or go ahead and just open your mic? Well, that's fine. That's fine. I got a question for you, Prajkta. Um, off the top, so in our program over the past, well, since like 2014, I'm trying to think of, I know for sure 2 studies that there are more, but I can think of at least 2 of our student studies off the top of my head that involved asteroids. One was last year's with St. Mary's. That was very kind of a geology type or geomorphology type study. In 2014, there was a team that looked at, I think what they had to do for the most part was went through and looked at papers. So they went and looked at the literature to find compositions of different meteorites. And they, in doing so, they were able to group certain meteorites and come up with like a potential family of asteroids that these could have come from. Now so it's one thing to be able to use different software that's currently available to do a geomorphological type of analysis like St. Mary's did. It's a whole other beast to dive into the literature and search for compositions of meteorites. So, which leads me to like, I guess more of a comment or a request for you is, so there's a meeting in November in Tucson about astromaterials data management. And I'm wondering, is that because there is data out there? There is chemistry data out there on meteorites, but they're all scattered in the literature. And there's not like one place where people can go and get that. Is that what we're doing? Hopefully in November is to start doing that.
Oh, absolutely. Actually, that would be such an amazing resource if we can do that. So I talked a little bit briefly about pre-solar grains. A lot of that work was done at WashU in Missouri, because the instruments at the time were rare. There was only like Nanosims that could do this kind of analysis. And that was the first lab in the United States to have that instrument and do that kind of study. And there were a few other places much later. So they maintained a really good database of pre-solar grains, and it's available online. You can go download things and do that. But I study CAIs, and there is no central database like that for CAIs and isotopic composition, because there are so many labs all over the world that have been doing this and collecting data, publishing it in papers, but there is no central database to discuss this, unfortunately. So hopefully, I mean, if you can get all the data, CAI is just one object that that has studied so much. But then there are con rules, then there is bulk composition of different meteorites. There are certain papers that sometimes do that, but we don't really have different planetary bodies. And like you were discussing earlier, like even for moon, like no central database for all this isotopic data or elemental data that's available in the literature. So yeah, that could be one of the very ambitious projects, actually. There is a lot of value to it. Yes, definitely.
Yeah. Okay.
Yeah.
So so at this point in time, then, if somebody were wanting to do some type of meteorite study that would be more cosmochemical in nature or mineralogical in nature, it's going to really rely on digging through literature.
Yes, if you do have advisors who do this kind of study, they may have some data that has already been collected, and students can help with those kind of things too. Like for example, since the pandemic happened, I didn't have access to the labs, so I was working with my boss at NASA JC, and we already had these elemental X-ray maps from some meteorites. So all I did was just sit in front of my computer, combine these maps, and create a mosaic, and then trace down all the CIs and conduits that I found on them. So the reason to do this is we wanted to see what is the size distribution of chondrules and CIs, the centimeter to millimeter size objects in this particular meteorite, and how does that compare with like other meteorites. So that is something that can be done too. Sometimes collecting data is an enormous task, but even understanding and interpreting that is also complicated. So that's something that if you do have right mentors who are interested in those sort of things, those could be little projects, like compact enough projects with some sort of outcome at the end of the academic year that students can think about.
Yeah. Okay, great. Anybody else online with us have any questions? or just need some time to digest.
Yes, I understand that it's a lot of jargon, and sometimes you get used to it, like someone like me gets used to it and then doesn't realize that this is something I should explain. So I'm hoping if there are any questions, please reach out. I don't think I put my email ID on the main slide, the first slide, but and if you could share that with people, I'm happy to answer questions if people have.
Yeah, when I send out the links to the recordings, I'll include you and Pravati's email addresses also.
Perfect.
Oh, here
I
we go.
know with the moon, with moon rocks, you can actually get the moon rocks to your school if you go through a whole process to do that. I've done that before. Is there such a process for meteorites?
Yes, actually, there are multiple places that do like these loan kits of meteorites. And meteorites are not as precious as moon rocks, though they are very precious. But many of the ordinary like chondrites and stuff you can buy online on eBay or Amazon. And many academic institutes like museums, etc., have these kits that they can give out for loan for educational purposes, that can be then, like, used for teaching in classes.
Yeah, so they're good for use in terms of, like, showing an example of a type of meteorite or something, but it's not something you would get for study.
Yeah.
If that's where you're going with your question, Sharon.
Well, in that case, if you do team up with a scientist, I mean, you can definitely email or do sample requests to like the meteorite collection that we have at JC, or there are some other like university-based collections or museum-based collections for analysis. So they would be on loan, and then you can send them back. But then you would have to provide a detailed analytical plan, and why do you need them? What do you need to do with them, etc.
Well, and wouldn't that also then require the instrumentation to?
Yes.
Yeah.
That's true.
There's that little detail.
Yeah.
Maybe one day, one of my grand visions for this program, should it ever come to fruition where this could be possible, is to actually have a scenario where students could apply, for a sample, a meteorite sample or a lunar sample even, and be able to work with a scientist somewhere where they just send the sample to the scientist, and then the students can just get the data after the fact. I mean, that something like that would be pretty cool. But I also think we would need more time than just like 6 months.
Okay. Well, some of the instrumentation is easier than others, so it depends on what you choose. Like one of the examples that actually I would like to give, I don't know through which program, but I have a friend who's a postdoc at UCLA, and she also studies CAIs, but she studies them in ordinary chondrites. So like the samples that I study, one thin section of, like, say a couple millimeter size would have many CAIs. For her, it's really difficult to find them. So what she does is she takes these automated maps on the microprobe, and then she's working with high school students basically to identify these CAIs, and it's basically a lot of data mining where she collects the data and the students are helping her to interpret that data and analyze that data. So that's something that's also possible.
Who is that?
Emily Dunham. I'll definitely ask her what program she's working with, like what sort of outreach program.
Yeah,
but
sure.
She's an independent postdoc.
Oh, okay.
Yeah.
Okay, cool.
Mm-hmm.
Okay, and Michelle had asked in the questions here if the slides for these PowerPoints have been made available, and they will be for this one and the moon presentation. So you'll all have those, and plus they'll be here in the recordings too. So, yeah. All right. Any other questions?
I have a question. A couple of slides back, you mentioned organic materials. So I was just wondering if you could talk more about that just a little bit. Like, what type of stuff are you? I'm sorry, it just really interested me. But I just was wondering what type of materials you guys are finding.
Right. So that's a very interesting question, and I'm going to give you very limited understanding of me because I don't study organics. This is not really my expertise, but analyzing organic materials in meteorites is really, really hard because it's very easy to contaminate them. So you need to find meteorites that are very pristine, they're false instead of fines. And then there are different kinds. There are some soluble organic materials or insoluble organic materials. As far as I know, you can study like different isotopic composition, elemental composition of these meteorites. I could probably give you some basic reading material if you're really interested in that. Do you have any specific questions about organics and meteorites?
No, I was just interested, like when the slide came up, it kind of like sparked my attention, but thank you. That was.
I can definitely find some basic. One of my favorite things are book chapters to read from when it comes to introduction to meteorites is this book called Cosmochemistry by Hap McSween and Gary Huss. So if you can find that somewhere, it's like college level, but it's pretty understanding. It could be like understood by high school students too. It's not. It may have some jargon, but it's actually very easy to read. So if you can actually find that somewhere, I'm pretty sure it has a chapter on organics in it too. Yeah.
Thank you.
And if you just want to read about an interesting meteorite controversy, look up ALH 84001.
Yep.
That was one of the Martian meteorites that had the fossils.
Yep.
All right. Well, thank you again, Prajkta, very much for giving this presentation. We'll have the recording posted online. It'll be on YouTube. I'll forward it to everybody along with her email and the. I'll figure out how to get you the slides. I may just go ahead and just do them as PDFs because that way it's a pretty small file that way. But we will share all that out.
I don't have control. Andy, could you like request share screen or something here so that I can get out of this? I can't move my cursor now.
Let's see here.
Oh, wait.
There you go.
Perfect. Awesome.